Module 1, Lesson 4, Equivalent Ratios. So this will be our second lesson on equivalent ratios. And taking a look at some learning targets here, we will once again be focused on this third learning target. I can reason about comparisons and make predictions about what would happen if part of the comparison changes. By comparison, we mean ratio. I can reason about ratios and make predictions about what would happen if part of the ratio changes. So in ratios, we've got two parts. So what would happen if this first part changes from a 2 to a 4? What happens over here to the second part? And of course, that would be a 6. All right, I can statements for this lesson. I can find equivalent ratios for given ratios. So we will be given a ratio, and we will need to come up with an equivalent ratio. And of course, I would expect you would be able to explain your process. Why did you do what you did? Why does it make sense? I can examine a set of ratios and figure out which ratios are equivalent using tape diagrams or other strategies. So if we're given 3 different ratios, we can say, are any of these equivalent to each other? And then we can also find a constant value, and we're going to use little lowercase c here, used to create equivalent ratios. And we'll take a look at what that is. All right, example 1, the morning announcement said that 2 out of every 7 6th grade students in the school have an overdue library book. Jasmine said that would mean 24 of us have overdue books. Grace argued, no way, that's way too high. And the question we're answering here is, how can we determine who is right? Not who is right, but what process would we go through to determine who is correct? So what we've got to do here is we've got to think about this. It says 2 out of every 7 6th grade students. So we know we've got a ratio of 2 to 7. And Jasmine is saying that is 24. So the 24 would be the number of students that have the overdue, and we'll set this up on a table here. So we have overdue and not overdue. Oh, wait a minute. Boy, I almost made a mistake right there. Overdue, and this 7 here represents the total number of students. 6th grade students, the total, and the overdue is the 2. To answer this question, we're going to have to know some information. We know that Jasmine is arguing that 24 have overdue library books, but we don't really have enough information to know whether or not Jasmine is correct or Grace is correct. What we don't know is what is the total number of students. To make a determination, how can we determine who is right? Well, we need some more information. We need to know what is the total number of students. And then we can check and we can see, is 24 to this total number of students equivalent to the 2 to 7 ratio? So we need some information if we are going to determine who is correct. Now, we've got a situation here where if Jasmine is going to be correct, we know that we were multiplied by 12. To get from the 2 to the 24, we multiplied by this 12, which would mean the 7 would be multiplied by 12, and we would know that it was 84. So if the total number of students is 84, then we know that Jasmine is correct. If the total number of students is less than 84, then we know that Grace was correct. That's way too high. That ratio would be off. If the total number of students is more than 84, wait a minute, I think I just said that backwards. If the total number of students is less than 84, then Grace would be correct. It's way too high. It must be a morning here. And if the number is greater than 84, then Grace would be incorrect. The number is not too high, and Jasmine would also be incorrect. So to know, how could we determine who is right? we need to know what the total is. So to make Jasmine's statements true, and we already looked at this, 2 to 7. So this is the number of overdue books, and this is the total number of students. And we're going to scale up to 24 for Jasmine's statement. And we know that we multiplied by 12. And as we learned in the last lesson, we have to multiply both parts of the ratio by the same number. And we would find out that there would need to be 84 students for Jasmine's statement to be correct. All right, so we are now going to look at some pairs of ratios, and we are going to answer some questions. First, we have to determine if these pairs of ratios are equivalent. Is 6 to 11 equivalent to 42 to 88? And if the ratios are not equivalent, we have to find an equivalent ratio. If the ratios are equivalent, we need to figure out the value C that could be used to multiply each number of the first ratio to get the numbers for the second ratio. So if we say these two ratios are equivalent, what did we multiply the 6 by and the 11 by to get 42 and to get 88? All right, so first question. Are they equivalent? Now there's a few different ways you can look at this. I'm going to first set it up as a table. So I've got the 6 to 11, I've got the 42 to the 88, and my question is simple. What is the 6 multiplied by to get to 42? What did I multiply the 6 by so that I could get to 42? Well, I know that 6 times 7 is 42. I come over here and I say, okay, if these are equivalent ratios, then this side also has to be multiplied by 7. 11 times 7 is 88. I don't think so. So are these two ratios equivalent? This side, the 6 and the 42, I've got to times 7. This side, the 11 and 88, I don't have a times 7. These are not equivalent ratios. Now, I do need to write an equivalent ratio. Well, I know 6 times 7 is 42, so I can put a 42 there. And I know that 11 times 7 is equal to 77. Now I have an equivalent ratio. All right, let's take a look at the next exercise here. I've got a ratio of 0 to 5 and a ratio of 0 to 20. And once again, I'm going to set these up in a table format so I can look and see what's happening here. To get from 0 to 0, nothing changed, right? So what did we multiply by? Well, we would multiply by 1. Or I could multiply times 0 and I would get 0. So I've got a couple of options there. What would happen on this side? Well, if I multiply times 1, I would get 5. If I multiply times 0, I would get 0. So I'm not so sure that this one's going to work here. But I have one other thing I can check here. You see, this left-hand side here with the zeros is kind of tricky. I can multiply anything times 0 and still get 0. So maybe I need to look over at this right-hand side for a second and do a little bit of thinking. What would I multiply 5 by to get 20? You see, over here with the zeros, I've got tons and tons and tons and tons and tons of different things I can multiply by. Over here with the 5 and the 20, I probably only got one thing that I could multiply by. So I need to check that. So I know that 5 times 4 is equal to 20. And I'm going to come over here and I'm going to try the times 4. 0 times 4 would give me 0. That would work. So yes, these are equivalent, and the value of C that I could use, what I would multiply both sides by, is 4. So it's important that we don't just look at one part of the ratio, but we check both parts of the ratio. All right, next exercise here, exercise 2. In a bag of mixed walnuts and cashews, the ratio of the number of walnuts to the number of cashews is 5 to 6. I hear a ratio statement here, and then I see an actual ratio. I've got my ratio language. Okay, it says determine the number of walnuts that are in the bag if there are 54 cashews. I'm going to set this one up with a tape diagram. Oh, there it says use a tape diagram. Okay, so I know I've got a ratio of 5, 1, 2, 3, 4, and 6. And I've got walnuts here, and I've got cashews here. Now let's not write over the top of things. All right, so this will be my walnut section. This will be my cashew section. There we go. It says there are 54 cashews. And I am trying to figure out what is the number of walnuts. Now, by drawing a tape diagram, I am able to see some things that are happening. I know that the total number of the cashews, all of this together, is 54. But I also know that it has been divided into 6 different parts. So that tells me 54 divided by 6. I've got 54 total, and I'm going to divide it by 6, and I'm going to find out that each part, each unit in the cashews is a 9. And yesterday we hit this really hard. When we're working with ratios, all of the parts are the same size. We've got a 5 to 6 here. Each of the 5 parts is the same size as each of the 6 parts. So all of these will also be 9. And I've got 1, 2, 3, 4, 5 of them. 9 times 5 gives me 45. So I have 45 walnuts, and I've got 54 cashews. Now I need to take a moment and actually show that my new ratio is equivalent. Well, I'm going to do a little erasing off on the side here, and I'm going to set up my table real quickly. I kind of like this. So I've got my walnuts and I've got my cashews, and I know my ratio is 5 to 6, and my new ratio is 45 to 54, and I multiplied both of these times 9. So I am showing the ratio that I started with, this 5 to 6. I'm showing my new ratio. I am showing that I multiplied both parts of my ratio by 9. So my C value, my little lowercase c, is 9. And you'll remember that's one of our I can statements, that we can find those C values, what both parts of the ratio are multiplied by. All right, exercise 3. And I know this one isn't in your math workbook, but I wanted to work on the I can statement if we could just look at some ratios and decide which ones are equivalent. And the question is, which of these are equivalent to 4 to 6? And it says, justify your answer using tape diagrams or some other strategy. Well, the first one I'm going to take a look at here. We've got 4 to 6, and I want to look at this 6 to 10. And this one's tricky. What can I multiply 4 by and get 6? Now, it might be helpful to think about multiplicative values from that first lesson that we did, but how many of you are really struggling to say, I can't think of anything that I would multiply 4 by and get 6? Some kind of fraction, isn't it? So I'm going to set that one to the side for a moment because, boy, my brain sure hurts. And let's look at a different one. So we've got 4 to 6 and we've got 2 to 3. This is our second ratio here. And this one, instead of a table, I want to set up as some tape diagrams so we can see what's happening here. So I've got 4 to 6, 1, 2, 3, and I've got 6, 1, 2, 3, 4, 5. And the question is that equal to 2 to 3? Well, I've got a couple of different ways that I can think about this problem. One of them would be to actually draw a tape diagram of 2 to 3. And to ask myself, is there anything that I could do with this 2 to 3 to get it to be 4 to 6? Right now, the value in each of my boxes is 1. Is there a number that I can put in all of my boxes? Is there a C value, something I can multiply by, that I could get 4 to 6? Well, if I put 2 in all of my boxes, now I have a 4 to 6. So my C value here is a 2. But here's another way I could look at it. I've got my 4, and I've got my 6. Can I make some groupings that are the same size? Can I combine some parts so that I have 2 and 3? Well, I can take this and combine them together, and my 4 now has 2 parts. So I'm making groupings of 2. If I make groupings of 2 here, now I have 3. So inside of my 4 to 6, I can make some groupings of 2 to 3. So 2 different ways I can look at that ratio of 2 to 3. All right, let's check out 16 to 24. Now that is an awful lot of tape diagram to draw there. So I'm going to set it up as a table. And I'm going to put the 16 and the 24 first. And I'll put the 4 and the 6. And here is the question that I want to answer, and this is what I modeled with the 4 to 6. Instead of multiplying, we're going to make groups. And when we make groups, that is dividing. I left a box off there. So the question is, if I have 16 of something, how am I going to group it so that I end up with 4? If I've got 16 units and I want to get 4 groups, what do I need to do? Well, I will divide by 4 to get to 4. And if I've got 24 and I divide it by 4, do I get 6? And the answer is yes, I do. So now we're stepping into this idea that not only are we multiplying by little c, but we could also divide by little c. And this comes up much more in a later lesson, but I felt like this was a great time to take a look at it. So 16 to 24 and 4 to 6 are equivalent. There is a value that I can divide 16 and 24 by, and I will get 4 to 6. So now we've got 9 and 15. So we've got a 4 to 6, and we've got a 9 to 15. And we're back to kind of this same problem here. What in the world am I going to divide by or multiply by so that I can get 9? Is there anything that I could multiply 4 by and get 9? And this is where I want to leave this problem. I'm going to say that 6 to 10 and 9 to 15 are not equivalent. The real focus is looking at the 2 problems here, the 2 to 3 and the 16 to 24. One more reason that this isn't in your workbook, so that we can have a discussion in class about these different problems. We will later on talk about strategies for working with 6 to 10 and 9 to 15. All right, so question, how can we use the description of equivalent ratios to find an equivalent ratio? Oh, come back here. So the description of equivalent ratios means that they have the same value. Well, how does that help us? Well, if we've got a ratio of 2 to 3, and we are testing to see if 4 to 6, we are asking, what did we multiply both of them by? Equivalent means equal value. Now, I showed this in class yesterday. I didn't show it in the video. But we talked about if you've got the ratio of 2 to 3 and you multiply by the rate by 2, but it's not by 2, you're multiplying by 2 over 2. This fraction right here is equal to 1. When you multiply by 1, the value doesn't change. So when we're multiplying by these 2's here, it's the same as multiplying by 1. The value doesn't change. And we also have this description from other lessons. Two ratios, A to B and C to D, are equivalent if there is a non-zero number. So A to B and C to D are equivalent if there is a number. Remember, this is our little c, the number that we multiply by. So I can take this A and multiply it times little c, and I get the big C. And I multiply B by the little c, and I get the big D. We covered that definition yesterday. So if there is a number right here, a little c, that I can multiply by, and in this video I showed you, hey, we can divide by 2. If I can divide A and B by little c and get big C and big D, it also works. What do the numbers in the boxes of the tape diagram represent in terms of the ratios? So we have 2 to 3, and we were putting numbers in the boxes. Now hopefully by now your brain has said, hey, the numbers in the boxes represent that little c, that number that we are multiplying by, which we might also call a constant. But that's a little bit of brain busting at the moment. That little c, this number here is the number we are multiplying by. Or, like I showed you with the 4 and the 6, it is also the number we can divide by, the size of the groups that we can make. So inside each of the boxes, the non-zero number c comes from the value of 1 unit in the tape diagram. Okay, what is true about the value of the numbers in the boxes of the tape diagram? They all have to be the same. The value of 1 unit in the tape diagram is the value of all the units. And they can be described as a constant. It doesn't change. It's constantly the same number. If I have to have some boxes that have 2's in them and some other boxes that have to have 3's, then I don't have equivalent ratios. All right, so I can statements. Hopefully you're feeling pretty comfortable now with finding equivalent ratios for given ratios. In particular, we're multiplying by little c. We'll talk more about the division thing later. Examine a set of ratios and figure out which ratios are equivalent using tape diagrams or other strategies. We looked at a couple of different strategies there, organizing with table to determine the constant c. We looked a little bit at some division stuff. We did not dive too much into really hard or difficult ratios. There were a couple of examples there that were brain busters, but we'll hold on to those. And then find the constant value c used to create equivalent ratios. We've been looking at this constant value. Today we were a little bit more explicit and pointed it out. All right, learning target. So I can reason about ratios and make predictions about what would happen if part of the ratio changes. So if I've got a 2 and it changes to an 8, I can say, well, that means we multiplied times 4. The other part of the ratio might be 9, and so I know this part is 36 because I multiply by 4. Therefore, these two ratios are equivalent. All right, that concludes Module 1, Lesson 4. Big lesson, important lesson. I know that in the video I have wandered through a few other things, but hopefully those are things that you can think about, things that you won't stress about, but use them on down the road. So if you've got questions, make sure you get with your teacher.